All right, might help if I turn the TV on. Let's get started. So a couple things while the TV and whatnot is getting loaded up. So I've got homework 4 graded, and before you all start saying, "Oh, let's add another to the list of mistakes," I corrected it before, got it corrected before class. There was a mistake in the solution, so there was a lot of people that got a point taken off that shouldn't have. So for instance, your grade on the homework, if it says something like 36 out of 40, but there's a +1 on the bottom of the sheet, your grade's actually 37 out of 40. You see what I mean? And I'll show you what the mistake was, but I caught it and got it taken care of. So, oh, what's that? We will have an exam. Oh, exam 1. Well,
So you did make another mistake.
well, that's a small one. Oh, you sure you want to do that? Because I'll change all the problems up and everything. Or we could have it comprehensive, so it has exam 1 and exam 2 material on it. What's that? I told you that it wouldn't be comprehensive. Goodness. There you go. So as I pass this out, let's see. So there you go.
Thank you.
No problem. Miss Davis. Pass that, Miss Davis. That goes to you. That goes to Miss Brownie. So again, if you see that +1 on the bottom of the homework, that's taking care of that little mistake. And the grades are reflected as such on Blackboard, so everything's kind of been taken care of, Mr. Lewis. I'll show you here in a second. Mr. Mason. Mr. Mays. Mr. McCracken. Mr. Mitchell. What'd you say? Mr. Schaffer. Where he was here. Oh. And Mr. Watson. All right, so real quick, before I pull up the solution, a couple things. So your homework 5's due on Friday, March 10th, and I didn't actually explicitly tell you what electrodes to use on that homework, so just go with E70. So I've got that here. Exam 2, March 15th. Don't forget that. We'll have review on Monday. We'll have the exam on Wednesday, and then assuming no snow between now and then, we'll cancel class on Friday. Sound good? Okay. Let me briefly pull up the solution, and like I said, I think everybody did pretty good, or pretty well on the homework. I'll show you the mistake where all the +1 stuff showed up, and it was really right here, and I'm going to pass out a copy of this solution real quick. But if on problem 1, if you notice, there's 2 cases of bolt bearing, and so there's the bolt bearing for the W section and the bolt bearing for the plates. I had the wrong FU value right here, so it was just a typo on my part. But the TA didn't know any better, so sort of deducted for everybody, just sort of grading each problem 1 at a time. So when I noticed it, I emailed the TA and said, "Hey, can you fix that?" And he did. So if you have a +1 or something like that on the bottom of your homework, that's where that is. Okay, so if you see something like wrong FU marked on your homework, it should have been corrected. All right. In the meantime, let me at least go through and pass out the solution. I'd argue this solution is probably a little more hefty, or in terms of the next test, than the solution for homework 5, since it's only 1 problem. 2, 3, 5. There's that. 1, 2, 3, 4, 5, 6, 7. 4. 1, 2, 3, 4, 5, 6, 7. Here we go. And 2. Mr. Lewis. Okay. So I think the big thing with this homework was that it was pretty repetitive, but it sort of is the nature of the beast when it comes to bolted connections, because you end up checking it bolt bearing at least twice, and it's sort of the same thing on both checks. One of the things I think probably gave a few of you few of you for a loop a little bit is if you check the bolt shear capacity of the connection, you get something like 286 kips. But if you check bolt bearing, I mean, you're getting some crazy numbers like 994 and 876, and that's fine, okay? Because all that means is that if you start loading this connection, the bolts fail first. That's all that means, okay? There's nothing wrong with that check at all, okay? So the actual capacity of this connection would be the 286. You don't know that until you go through and do the math and check it out. I'd say that connections that have a large number of bolts, I'd say it's a pretty common instance that bolt shear governs, because there's a lot of bolts means there's a lot of plate you got to fill in order to fail that connection. Okay, so that's problem 1. Now, I imagine on problem 2 that there's probably going to be some differences on the actual connection layout. In other words, do you use the minimum bolt spacing or do you use the preferred bolt spacing? And what I wanted to show you is in my solution, I use the minimum, because if you use the minimum, first off, you get nice, easy dimensions. They're all 2 inches and 1 inch. It's pretty straightforward. But I wanted to show you that you can use minimum, and minimum will work from a bolt bearing standpoint. So if S minimum works, S preferred is obviously going to work. So here's the trial connection design. There's 6 bolts. The edge distance is 1 inch and the bolt spacing is 2 inches. If you go through and do the bolt bearing calcs, you only need to do it on the center plate because there's a lot less thickness of material in that center plate as opposed to the angles. You find that when it's all said and done, it works. Now, some of you look at these 2 numbers and you go, well, gosh, that connection's not very efficient. But when you do that, you're forgetting that there's bolt shear, bolt slip, and bolt bearing. Now, the value that governed the design of this connection, if I remember correctly, was bolt slip. Okay. Now, the capacity per bolt is something like 19 kips. So what's 19 times 6? What is it? 60 and 54, so that's 114. So the actual governing capacity of this connection is 114 kips. So take 100 and divide it by 114, and there's your efficiency. Now you can find that bolted connections, they are, by their very nature, a little less efficient than a typical member design. I mean, when you do the math, you find that you need 5.3 bolts, so you round that up to 6. You're actually rounding that up quite a bit. So you can find that your efficiency for connection design can be, especially with bolted connections, can be a little lower than you'd like, but it's really just sort of the nature of the beast in regards to bolted connections. Does that make sense? Everybody okay with that? Problem 3, I think as long as you were being diligent in your numbering and your naming and your labeling, problem 3 was pretty straightforward, pretty plug and chug. You find that the connection is adequate. Does anybody have any questions at all about any of this? And it would have worked. Did you get docked?
Yeah.
You did get docked.
I S preferred, so I got something different than what's on here. So then it changed my.
I wasn't aware the TA did that. How many of you used S preferred and got docked? But you got docked. I need like hands raised. How many? Just 2 of you? All right. You come see me a little bit after class. I want to look at that because you shouldn't have gotten docked. I mean, it doesn't matter. It doesn't matter. He's a human being. If he made a mistake, I'll be happy to fix it. All right. Sound good? All right. Everybody else good? Okay. So are there any questions on the welded homework? I'm just curious. I get the feeling not everybody started it, but it's a really short homework, so it should be pretty straightforward. Everybody good? Bless you. All right. If that's the case, I do want to get into to columns today. I'm going to go ahead and just level with you. Things get a little different in here, starting with columns and beams. I would argue the analysis, the design aspects associated with columns and associated with beams are a 180. We're entering a little bit of a different world. I'm going to have to bring up a little bit of the C word, a little bit of calculus, but it won't be so bad the way that we handle it. We enter a whole different type of discussion starting now and throughout the rest of the semester in regards to columns and beams, because we now broach into a completely different topic of structural engineering, and that's the topic of stability. We've been talking about, up until now, things that are being yanked on. Tension members, even if you're talking about bolted, welded connection, you essentially, regardless of the complexity associated with the geometry, in the end you have, a series of plates going this way and a series of plates going this way, joined with either bolts and welds, and they're being yanked on, essentially, in some fashion. That's the nature of tension members and bolted and welded connections. And ultimately, our limit has really been something like fracture or bolt shear or something like that. And the design aspects have been pretty straightforward. I mean, say what you will, but theoretically, the design of a tension member is pretty simple. You have the load, you have the stress, divide to get the area, right? That was really it. You have bolts. Have the load, capacity of one bolt, divide to get the number of bolts. It's pretty simple. Well, that stops right now, because with compression members, it's not so simple. Things that are in compression like to do stuff that things in tension don't like to do, specifically things in compression like to buckle, okay? So we need to talk a little bit about buckling and how we have to adjust our theory to handle real-world behavior. So we're going to find a term pop up that we've seen before, and it was just sort of a passing thought, which is going to become really important to us now. Things in compression like to buckle, and specifically a column's strength is a function of its slenderness. You remember how we defined slenderness with tension members? How did we define slenderness? L over R, okay? Now, that's the same thing for us in columns. Although specifically it's going to be KL over R because we adjust that by the column's effective length. But slenderness is really going to be a very important parameter for us. And we're going to find that columns behave differently depending upon their relative slenderness values. For instance, I would say columns that are short are the only columns that can really be loaded to the yield stress. The longer a column gets, the weaker a column gets. And that wasn't the case with a tension member. We didn't really care how long the tension member was for its capacity. I mean, the capacity of a tension member was 0.9 FYAG and 0.75 FU ANU. The length didn't matter, okay? For columns, that's going to matter, okay? And we're going to have differences between whether or not a column buckles inelastically and whether or not a column buckles elastically. There are going to be differences in behavior. But before we even get into that, we got to go into buckling. Now, if you had me for deformable, we did talk about buckling at the end. If not, no big deal. I do want to at least go through some of the basic theory. So, you imagine you've got a yardstick in your hand. You take that yardstick and you push on it. The yardstick tends to want to bow out, right? You push it, and whoop, it starts to bow out. That sudden loss of strength is what's called buckling. Buckling is a geometric loss of stiffness due to loads and compression. By and large, that's a general description for it. It's an old idea. I mean, it was the equations for Euler buckling were derived back in the 1700s, so it's not a new concept. Some of you have you probably remember the equations for Euler buckling. Now I'm going to show them to you, and then I'm ultimately going to show you why they're wrong. Or wrong's maybe a bad word. Maybe the best word is they're not accurate enough, and we'll go into why that's the case. But first off, let's just sort of go back to basics. So let's consider we have a pin-pin column. So instead of a pen beam, we're talking about a pen column that's being loaded in compression. So that column has some length L. It has some modulus of elasticity E and some moment of inertia I, right? So I've got some load on it, and I want to determine the amount of load that will cause that column to buckle, right? Now, would you agree that if I load that column in compression, that when it buckles, it's probably going to look something about like that? Fair statement? Okay. So that's number one. Number two, if I've got P going down, statics tells me I have to have P going up. Fair point? Okay. All right. So you know me, my favorite weapon is a samurai sword or a lightsaber, or in this case a K-cutter. I cut right through the column. I'll cut right through the column at some distance x from the bottom, and I get a situation that looks something like this. So statics tells me that if I've got P going up, I've got to have P going down. But because this column is deflected out a little bit, I'm proposing that there's a little bit of moment in that column. And that moment is directly proportional to how much it's deflected out. You know, if I cut a section, that column is deflected out, we'll call it some distance y. So if I sum moments at the cut, I've got some moment going like this, and I've got P at some distance y going like that. So the moment inside that column is P times y, or negative P times y because of our sign convention. Everybody okay with that? Any questions? All right. So let's go back to some basics. Now, whether or not you had me for deformable or not, you definitely had me for structural analysis, and I know you remember that the second derivative of deflection is m over EI. It was a very fundamental relationship that we established in structural analysis to be able to determine deflections in beams. Well, I mean, we're still talking about the same scenario. We're still talking about an element undergoing bending deformation. So the second derivative of deflection is m over EI. Everybody remember that? I know you remember that. You're giving me that look. You remember that. I know you do. All right. Yes, you do. Yes, you do. So if the second derivative of deflection is m over EI, and m from our equilibrium analysis was negative Py, I can plug and chug and I can get this. Everybody okay with that? Now, I'm going to take this equation and I'm going to simplify it a little bit. I'm going to move this all over here, right? So I've got y double prime plus P over EI times y equals 0. And just to make the math a little simpler later, I'm going to take that P over EI and I'm going to define an arbitrary constant. I'm going to call this alpha squared. So what that's going to yield is this, a second order differential equation. Second order because we got two derivatives. Okay? Everybody all right with that? Okay. Now, I see some people going, no, sir. So, for instance, you've got a second order differential equation. You've got a number of methods that you can use to solve this differential equation. I'm going to use the one that I think is most popular among college students. So, let's see. So, acting like I don't know things. I know things. All right. So, y double prime plus, and since I don't have alpha, I'll just call it A. And here we go. As I started typing, it's already built in. Okay? This is a very common differential equation. Y double prime plus A squared times y equals 0. So now if you want, you can actually do the mathematical, process. You can write your characteristic equation, get imaginary roots, and recognize that imaginary roots are conjugate pairs, sines and cosines, if you've had differential equations. But I don't know about all that. No, I'm good. I made it through differential equations once. I'm sorry. Well, I'm good. No, but in all honesty, I'm being facetious, but in all honesty, this is not a very difficult differential equation to solve. It's pretty straightforward. Now, I propose that if you've got a differential equation in this format, then the solution is some arbitrary constant times the cosine plus some arbitrary constant times the sine. So the reason why I called that term alpha squared is because the solution yielded alphas. That's the only reason why I did that. All right. Everybody okay with that? Now, in the world of differential equations, when you have a solution for a differential equation, in general, it's an arbitrary solution. It is a function of arbitrary constants. In this case, it's the function of C1 and C2. Now, in order to solve for those arbitrary constants, I need some boundary conditions for the problem at hand. Okay? Now, here's the problem at hand right here. It's a column undergoing compression. Now, our boundary conditions for this diffie-q are that the deflection here and the deflection here are 0. I mean, those supports, that's what those supports are doing. They are restraining that column from deflecting at those particular points. Okay? Does that make sense? So we have two arbitrary constants, C1 and C2. We can solve for those by stating that the deflection at 0 equals 0 and the deflection at L equals 0. You know, x equals 0 and x equals L. Everybody okay with that? Okay. Now, here's our differential equation. Okay, here it is. Let's take care of the first one. So the deflection at 0. So plug in 0, so C1 times the cosine of 0 plus C2 times the sine of 0. The cosine of 0 is 1, the sine of 0 is 0, and I get that. Everybody okay with that? Okay. So this term right here, this term goes to 0 because that's 0. Now our second one, deflection at L equals 0. So plug in x equals L, all that must be equal to 0, and we get this. Okay? This gives us a few problems, okay, from a theoretical standpoint, because we have C2 times the sine of alpha L equals 0. Okay, this is an equation. Okay, C2 times the sine of alpha L equals 0. So for that equation to be true, a number of different things can happen, but a lot of these yield trivial solutions. For instance, for this equation to be 0, would you agree that that could be 0? The C2 could be 0? That's a possibility for this equation to be 0. The problem is that if here's my equation, and that's 0, and that's 0, well, there's no deflection, right? And we know that's not the case because there's what the column looks like, okay? So what I'm saying is that this indicates a trivial solution, okay? It doesn't really tell us anything. One way that this equation could be 0 is what if L is 0? Well, think about it. If L is 0, then you have the sine of 0, which is 0, right? But that indicates a column that doesn't have any length. That doesn't make any sense either, right? What about alpha? Well, alpha could be 0, but if you recall, this is alpha, so if alpha is 0, that's sort of indicating that the column doesn't have any load on it. That doesn't make any sense either, right? Now, what about this? What about this entire sine term? What if that is equal to 0? Well, maybe that's not so trivial. If you recall, the graph of the sine function looks something about like that, right? And the sine function equals 0 at integer values of pi, right? At 1 pi, 2 pi, 3 pi, 4 pi. That's where the sine function equals 0. So I can solve for alpha, and I propose that alpha equals n pi over L. That will tell us that critical load that will cause that column to buckle. So if here's alpha right here. I can square that, but then I know alpha squared is also P over EI. I can solve, just plug and chug and solve for P, and I can get a nice little plug and chug expression for the load that causes that column to buckle. And and we're going to see here in a second, since our first mode is the critical buckling mode, pi squared EI over L squared, that's our critical buckling load for a column. But is everybody okay with this so far? Okay. So recognizing that the sine function is the only one that gives us the non-trivial solution, we can plug and chug and get a nice little expression for deflection. Now these little n values are the only ones that I haven't really explained in detail. Each of those n values are associated with what's called a buckling mode. In other words, what the shape of the column looks like after it has buckled. So they're sort of arbitrary, but there's a very clear physical understanding if you get into it. So recall that this is essentially a bunch of sines and cosines. Well, if you set n equals to 1 and calculate not only the load, but the buckled shape, I mean our buckled shape is essentially a big sine function, it looks like this. So here's n equals 1, and here's the resulting buckling load. Here's n equals 2. Notice how we got, sort of 2 sine waves. So the column's sort of doing that, okay? And here's our resulting buckling load. Here's n equals 3 and our resulting buckling load. Everybody kind of getting the general idea? Now, if I actually just take that yardstick and start loading it, which one am I going to hit first? This load, or this load? The one on the left, center, or the right? The left. That's the smallest load. If I start pushing on it, that's the one I'm going to hit first. So what I'm stating is that right there, this is the critical buckling load for a simply supported column, pi squared EI over L squared. Now, I've got to believe, I know the folks who had me for deformable, you saw that probably near the end of the semester. It's been a while, but I know you've seen it, okay? Everybody with me so far? I know you've seen it. You may not remember it, but I know you have. Okay. Now, this is the buckling load, okay? The buckling stress, let's just keep it simple. Stress is P over A, right? So if I take this and I divide it by A, what I'm doing is I'm saying, okay, if I take this term and I divide it by A, I'm going to pull this term I out, and would you agree with this right here, this I over A? There's a very specific name for I over A, or specifically the square root of I over A, and we call that a radius of gyration. In other words, when we've been looking up these R values for L over R terms, R is just the square root of I over A, and we call that the radius of gyration. Okay? Everybody with me so far? This is stuff I know. It's been a while since you've seen this, but it is somewhat relevant. Everybody okay? Okay. So what I'm getting at is we now have a term not only for the buckling load, pi squared EI over L squared, but we also have a term for the buckling stress, which is just pi squared times the Young's modulus divided by this, which is just the slenderness squared. So far, so good? Now, we made a couple of assumptions when we derived this. So one of the assumptions I'm going to tackle right now is the boundary conditions. For instance, when we derived this column's capacity, or its buckling load, we assume pin-pinned, right? Well, what if it's not pin-pinned? What if it's fixed-free or fixed-fixed or something like that? Okay? I think it stands to reason that this column is going to behave differently than this column. Everybody okay with that understanding? Okay. Well, one of the ways that we can use this same theory is through the use of what's called an effective length factor. For instance, would you agree that this column, once buckled, probably looks something a little bit like this? Do you agree with that? Okay. Well, I propose if we can relate this to a pin-pin column, we can use the same theory. Now, I'm going to do that through the use of an effective length factor. And all the effective length factor, or K, all it's trying to do is it's trying to relate some random column, some arbitrary column, to that column. So this is sort of our baseline. So for this column, the K value would be 1, a pin-pin column. Well, what I'm getting at is I'm saying that K is trying to relate the distance between here and here, specifically trying to mimic that buckled shape on some arbitrary column, for instance, like this. In other words, if I took this column and sort of traced it out a little bit, see how I'm sort of repeating that buckled shape, kind of like that? Everybody kind of see that? So what I'm getting at is that the effective length factor for, let's say, this column would be 2 for a fixed free column. Because if I took that buckled shape and just sort of stretched it out, that distance between inflection points for this column would be twice its original length, since K is 2. Everybody okay with that? Okay. So that's where this K term, this effective length factor, comes into play. So this sort of modifies our theory a little bit. Instead of pi squared EI over L squared, it's pi squared EI over the quantity KL squared, or in this case, KL over R. So everybody kind of see where that came from? Okay. Now, if you go to the manual and notice, got my little star, got my little tabbed region. We're in 16.1-511. So this is actually really deep into the back of the manual. It's actually in the gray pages right back here. This is definitely something you're going to want to tab, okay? So what this does is it will list different cases for your columns boundary conditions, and then based on those cases, what are the resulting effective length factors, okay? For instance, look at the one we just did. The one we just did was case E. If you notice, case E is a fixed free column, okay? Notice how the theoretical K value is 2, okay? But that also brings up another good point. Didn't bring them.
I realized after I had walked out the door.
Wait, just after you walked out the door?
Literally. I was like, I'm already. And then I got here just barely on time.
Well, don't forget the tab. All right. One of the things that I definitely want to point out is if you notice there is a difference between a theoretical K value and a recommended K value for design or for our calculations. And the reason for the difference is if you notice the difference is always higher. For instance, instead of 0.5 we're using 0.65. Instead of 0.7 we're using 0.8. The reason why is because, let's be clear, these boundary conditions are not real. They're mathematical idealizations of what's going on. There's no such thing as a boundary condition that's perfectly fixed. That doesn't exist. That's just an idea. Okay? So instead of if we had a column that we were idealizing as fixed, yeah, the theoretical K value is 0.5, but to be conservative, we want to use a larger K value. And let's be clear, what happens when K gets larger? If K gets larger, this quantity increases, which in turn decreases my usable capacity. Make sense? Okay. Any questions? One final point is right now what I'm doing is I'm talking about columns that are by themselves, that are by alone, a single column. Later on, we'll talk about how do we compute K for a column that is inside a rigid moment frame. That'll be a loaded discussion in and of itself. Okay. Sound good? Yes.
I'm sure that this will come up eventually, but why would we care about the maximum stress which is finite load?
We will get to that. We will get to that. And I'm actually going to talk about that a little bit in the next slide. Okay. Everybody with me so far? Now, there's a couple minor issues, like if the load isn't through the centroid, if there's a little bit of twist. Yes, sir. You could, all right, and there's a very specific reason why we don't, okay? The reason why we don't is the term KL over R is unitless, okay? Because think you have a length divided by a radius of gyration. They're both in units of length, so they're unitless. So they make it really easy to express capacities. For instance, if you've got different geometry or different yield stresses, if you know your KL over R, then you can compute the capacity sort of any column. You see what I mean? Whereas if you start factoring that out, then you're looking at an individual column, not any column. Does that make sense? That's a good point, though, and that's sort of why we leave that there. Sound good? Now, there's a few minor things that that we can account for, like twisting and whatnot, which isn't really a major concern for I-beams or W shapes, and then loading through the centroid, which we'll talk about later. But by and large, everything I just discussed is stuff that you learned in 216 fundamental buckling equations for columns. And they're wrong. In other words, and in all honesty, saying they're wrong is not very fair. Saying that they're not good enough is incredibly fair, okay? The equations that I just mentioned, like these equations right here, if you use these equations by themselves to design a steel column in a building, it would not be good enough, okay? For two very, very major regions, nudge, nudge, wink, wink, very, very major regions, okay? I think you're picking up what I'm putting down there. All right. He didn't say von Mises. When did he ever talk about von Mises? All right. All right. The two big reasons why real column behavior deviates from ideal column behavior is, number one, the presence of residual stresses, and two, the presence of geometric imperfection. And they each affect the capacity of a column, which one thing I'll point out, I want to be clear, it's not like these elements are only present for compression members. I mean, they're there in tension members too. But the big issue is with tension members, we didn't care about buckling. Okay? Buckling, a loss of stability. And having a loss of stability is a real big issue. I mean, that's the issue with compression members. Like to allude to that, when I say the presence of geometric imperfections, what I'm saying is this. Are you telling me that every single column that comes directly from the mill and gets erected in a steel frame, are you telling me it is 100% perfectly straight? Or does it have a little bit of kink to it? I'm not saying, I'm not saying that the column's 12 foot tall and it's off by 7 feet. I'm saying that it's off maybe like 1/8 of an inch or 1/4 of an inch. It's a little imperfect. Would you buy that? Okay. If I take that column or if I take that element and yank on it, I mean, does it matter if I'm putting it in tension that the column is a little bit out of straight? Well, not really. But imagine that. Okay, let's do the same analogy if it's in compression. Okay. Now, let's say that I'm on top of a mountain. Okay. And Mr. Schaffer doesn't like me very much. So let's say that I'm on top of a mountain. Okay, and Mr. Schaffer decides to push me. Now he pushes me, I'm going to go like this, and maybe I can catch myself. Maybe. Okay? Now, let's take the same scenario, but now I've got an 80-pound backpack on my back. Okay? Now, here's what's going to happen when he pushes me. Okay? He's going to push me, and then let's think about this from a static standpoint. I have a load that's off center of gravity, right? Okay, which is going to cause some moment, which is going to cause some more eccentricity, which is going to cause more moment, which is going to cause more eccentricity. See how it builds up on itself? Okay, that's what's called a second order effect. Okay, and that it has a much more profound impact for an element that's in compression versus one that's in tension. I mean, if I have a member that's a little bit out of straight and I'm pulling on it, all the tension is going to do is help that imperfections because it's going to want to make that member become more straight. Make sense? So I guess the point that I'm making is I want you to recognize that these things still exist for elements in tension. We just don't really care about them. Okay? Make sense? Okay. But let's talk a little bit about each one of these one at a time. And I want to start off and talk about these things called residual stresses. Okay? So here is the equation for the critical buckling stress of a column. So pi squared E divided by KL over R squared. Now if I plot that, okay, so I'm putting KL over R on the x-axis and the capacity or the buckling stress on the y-axis. If I have y equals some constant divided by x squared, that's a hyperbola, right? So the plot of that capacity as a function of KL over R is a hyperbola. Everybody okay with that? Now, let's also add a little bit of reality to it. I mean, this is a hyperbola, so it goes up to infinity, right? You telling me that a steel column can resist a buckling stress of 946 KSI? No, right? It doesn't really make a lot of sense. So why don't we take that and just cut it off at the yield stress? You know, that sounds reasonable, right? Just cut it off at the yield stress. Okay. Now I can solve for that point, and I have a point I want to make for this. I can solve for the location where Fy equals this, and I get this term, this slenderness, some constant times the square root of E over Fy. And I really want to indicate that because we're going to see that quite a bit. Some number times the square root of E over Fy. Those are going to show up a lot as compactness limits later on. Okay? All right. So what we're ultimately doing right now is we're taking the, what's up? It just sort of squashes a little bit. In fact, the yield load for columns is sometimes called the squash load. I'm not kidding. That's a real term.
Butternut squash or spaghetti squash?
It smushes, but butternut's all right with me. So, but seriously, it just gets shorter. That's the same thing you would think would happen, but that isn't going to happen for like that column right there. It's too long. So we're talking about really short columns. Like I'm talking about a W14 section that's really short. Does that make sense? Oh, okay. All right. One point I do want to make is that we are taking this, would you agree this curve represents the theoretical capacity of a column, right? We're going to take this curve and successively change it to try and represent real-world behavior, okay? And if you look at compression members part 2, if you look at the next handout, like go ahead and turn to it and look at the first slide on compression members part 2. Right there, that is the actual column curve that we use in AISC. We'll get to why that is what it is, and we're sort of knocking that out one at a time. Okay, so you agree so far that that's a reasonable column curve. Okay, let's see if we can change that a little bit. All right, so let's look at our stress-strain curve a little bit. Now I'm zooming in a little bit to a particular region on the stress-strain curve. Up until now, we've just been assuming it's linear up until Fy, and then it just yields. But in actuality, there's a little bit of a transition region between when it actually reaches its full yielding and then when it reaches what we call its proportional limit. Remember, its proportional limit is when you start to get that onset of yielding, and then it actually takes a little bit of time for that yielding to progress throughout the section. Y'all remember that from like what, C321 from civil engineering materials? Huffman probably mentioned that to you. So in that region, instead of dealing with the full elastic modulus, the 29,000 KSI, we're dealing with a little bit of a reduced modulus that's just tangent off that line. So we call that tangent modulus. Okay? Now, that would be fine in and of itself if it weren't for the presence of residual stresses. Now, residual stresses are something that occur in a wide range of different manufacturing arenas. And in the world of steel production, particularly producing things like a rolled W shape, it primarily results from uneven cooling. Okay? When you buy a W10 by 49 or what have you from the steel mill, there's already stresses locked into it as soon as you picked it up from the mill, as soon as you picked it up from the shelf. Now, let's be clear, the amount of compression that's in the section has to equal the amount of tension that's in the section, otherwise the beam's running away from you. But there are compressive and tensile stresses already locked in there. Now, for W-shape, it primarily results from uneven cooling. And what do I mean by that? Okay, let's take an I shape. Okay, now let's be clear. How do you produce that? I mean, you're taking this, red-hot billet of steel and successfully running it through rollers to produce an I-beam, right? So you're successfully flattening it over and over again. So once it's done, that I shape is still kind of hot, right? Then it starts to cool down. But it doesn't cool at an even rate. In other words, these outstanding elements, like these little flange tips right here and these, like the center part of the web, they cool first. And they cool before these stockier components right here where the flange and the web come together. In other words, I mean, think about it. If I heated that up, the elements that are outstanding, that are the farthest away, they're the ones that are going to cool down the quickest. It's going to take a little longer for all the heat to dissipate out of that flange web junction right there. Does that make sense? So, I mean, go back to your mechanics. When things heat up, they expand, and when things cool down, they contract. But what happens is this element is contracting at different rates. So what happens is these elements right here, these outstanding elements, they go into compression. But in order to maintain equilibrium, these elements where the flange and the web come together, they have to go into tension to match out the equilibrium. To give you kind of a simpler idea, it's kind of like as the element is cooling down, it's undergoing all these stress changes. It's almost like the I-beam is going, and it's got these stresses locked in there, and those stresses are always there once from the time that the element is produced from then on. Now, again, those stresses were there for tension members, but we just sort of assume that we blow through them during the yielding and fracture limit states. We can't really assume that here for compression, and here's why. So this is just sort of a conceptual idea of what the stresses in an I-beam would look like, the residual stresses. The red regions are the ones that are in compression, and the blue regions are the ones that are in tension. Now, this is idealized. Don't take those images to the bank, but it's just trying to give you the idea that the amount of compression equals the amount of tension. Well, let's be clear. This is the element with no load on it. Now, here's what happens when I put some load on it. What happens is some of the elements, would you agree, are probably going to yield before others? That makes sense? Okay. Well, here's the problem. This would be the stress-strain curve of an I shape with no residual stresses. If we account for residual stresses, that's what the stress-strain curve looks like. Because yielding is going to progress throughout that section as we begin to load it, and that's going to cause a big issue. And the big point is that's going to cause a big issue from a stability standpoint. See, with tension members, we didn't care about buckling. So our 0.9 FYAG limit, we're talking about all the way out here. We really didn't care about whether or not it was going to buckle. In compression, that matters. Okay? So as we load this, your flange tips are probably going to yield first, then the center of your web, and that yielding is going to progress, and it's going to propagate throughout your section. The more that section yields, the weaker it is. Okay? Does that make sense? Anybody got any questions on that? Yes, sir. Well, you never want brittle behavior. Never. But your question's a little tough to answer right now. We will answer that later. Okay? I would say that we actually would desire more inelastic behavior than we do elastic behavior, but it's from an economy standpoint, and it's not easy to explain right now. Okay? We will get to that. Right. Everybody good so far? All right. So this right here is one of the big reasons why that Euler buckling formula that I presented earlier won't work. Okay? This is one of the big reasons right here. Okay? The other big reason is what I was mentioning earlier, the idea of geometric imperfections. Columns can generally possess two different types of imperfections. Number one, they can have an initial out of straightness. In other words, the column has some bow to it. Or they can have an initial out of plumbness. So here's the column, but it's off, a little bit. Again, we're not talking, a 12-foot column that's off 8 feet. We're talking a 12-foot column that's off 1/8 of an inch or 1/4 of an inch. I mean, you cannot tell me with specificity that there's no such thing as a perfect column. Okay, there's always going to be some level of out of straightness or out of plumbness. It's all about, is that out of straightness or out of plumbness tolerable? Is it within tolerance? So it is going to be there. Okay, the problem though is that initial out of straightness and out of plumbness is going to affect the capacity. Okay. So this would be the buckling curve for a column that's perfectly straight. That theory that I derived earlier when I used Wolfram alpha, okay, and went and solved for my boundary conditions, I'm using what's called a bifurcation theory. Okay. Now, a bifurcation theory, it basically states that the column is either buckled or it's not. So I'm loading the column, it's straight, and then I hit that magical load and suddenly it buckles. Now you probably kind of get that understanding. If you had a really rigid, perfectly straight column, it sort of suddenly buckles on you. But in actuality, that's not what really happens. What really happens is those deflections and those imperfections sort of build on one another. It's kind of what I was mentioning with the backpack. Kick over, a little bit of deflection, a little bit more kick over, and it sort of builds on itself. That's what's called a second order effect. the idea that those deflections, they build on one another. Okay? Does that kind of make sense? Everybody okay with that? And then if we add the fact that we've got inelastic residual stresses, the column's behavior gets even worse. So my point is this. When you take all that stuff into consideration, remember this curve right here? That was that cutoff curve that I mentioned earlier. This, see this solid blue curve right there? That is the actual curve that we use to compute the capacity of a column. So what I'm getting at is this. The capacity of a column is computed by taking the critical buckling stress and multiplying it by the area, and then multiplying it by phi. But to get the critical buckling stress, it's a function of, A, what is our slenderness, and whether or not we are in the inelastic or elastic range. We're going to spend a fair amount of time going into the column provisions later on. The only other point I would mention, and I'm going to mention this now, and I'm probably going to mention this a few times, this right here, where it says 0.658 and it says Fy over Fe, that is not 0.658 times that fraction. It's 0.658 raised to that fraction. So that fraction is the exponent. Okay? You are the man, because yep. Sign-in sheet. So here's what I'm going to do. I'm going to put the sign-in sheet right here. Some of you are leaving, so you can just sign it on your way out. And those of you that are in concrete can just sort of sign it between now and then. Does that sound good? All right. Next time, we're going to spend a lot of time going into the theory behind column behavior, or not the theory, but the applications of column behavior, how AISC handles column capacity, and we'll have a fair amount of time going into this. This will take some time to sort of appropriately explore this. Sound good? Hold on, let me, well, actually not really. If you want, you can tab that table. I have one there, but you really don't need one. So I'm going to go ahead and stop this since we're done here.